right, welcome to our second day of electric currents. So today we're going to be looking at a little bit more application-based information about electric currents. But before we get into today's information, let's go ahead and recap what we looked at last time. So last time we introduced this thing called current. So current was given by the variable I. It's the amount of charge per time. And when we're discussing current, we're going to be discussing the conventional current. So that is the direction of the positive charges. We now know that's wrong, but that's still something we do for tradition's sake, even though 95% of other physics isn't traditional. We looked at Ohm's law. Here I've put law in quotes because it's not really a law. But what it does is it takes the current that we have inside of a wire, and it says that the potential across the wire is going to be equal to the current times the resistance. So the reason that Ohm's law is in parentheses here is we're making the assumption that the resistance is constant throughout the entirety of what we're doing. And we looked at a couple of situations where resistance is dependent on temperature. So basically we are ignoring this temperature dependence of resistance when using Ohm's law. However, we can calculate the resistance at a higher temperature. If we were given enough information to do that, we would just keep it constant throughout the entirety of the time. So we're going to see current today, and we're going to see it as well all next week. And we're going to be seeing Ohm's law next week as well. But today what we're going to be focusing on is a little bit more application based. So in this first video, we're going to go over electric power as well as power in household circuits. In this second video, we're going to be covering alternating currents. And then in the third and final video, we're going to look at electrical conduction in the human nervous system. So 3 videos. So with the first and the third video, a little bit more application based. The second video, we'll talk about some of the little nuances of some stuff there. So let's go ahead and hop into electric power. So power was introduced for the first time in this sequence in chapter 6. And when power was introduced, this equation was used. It was the average power was equal to the work per time. Where here we know work and energy are related to each other, where work is a change in kinetic or potential energy. So work is equal to the energy transformed from one type to another over time. So this is just the introduction of power and how it was used originally when we saw it. And it had the SI unit of watts, which is 1 joule per 1 second. So what we're going to be building up to is trying to figure out how can we go from work to electric-based information. But right now we're just kind of recapping on power stuff. And so with electric power, something that we're going to be seeing rather frequently is kilowatt hours instead of joules. So when you have an electric bill, it's measured in kilowatt hours instead of being measured in joules. They are both measurements of energy. But they're not explicitly the same value. So, if you see kilowatt hours, you just need to multiply it by 3.6 times 10 to the 6, and that will get you to joules. And you will be using that transformation a couple of different times depending on the question that you're given. So in some questions in the textbook, you'll do your entire calculation, you'll get joules in the end, then it'll ask you to convert it to kilowatt hours. So this conversion is important in that regard. But basically what it is if we look at our SI units for power, it's watts. So here we have kilo, so 1,000 watts. So that's the kilowatt part. And then you have hours. So 1 hour is equal to 3,600 seconds. A kilowatt hour is watts times the hour, and that's how you get it to joules. Because again, watts is joules per second. You can go through the conversion to get rid of seconds and convert it to hours. That's how kilowatt hours end up working out. So a kilowatt hour is a measurement of energy. However, it's not an SI unit, so you will have to convert back and forth. So commonly with electricity, we are going to transform electric energy into thermal energy. If you've ever had to change a light bulb, the light bulb box comes with instructions to make sure that the light bulb hasn't been on for a while. If you've ever accidentally touched and exposed, your phone will heat up as it charges, your laptop heats up as it charges, the little, power converting box does that. It's because a lot of electric power is being transformed into a thermal energy. So here we have a new equation for our power. So power is still the energy transformed over time. That is remaining the same. It's just how we're looking at the energy is going to be changing. So here we have charge times potential. And this was just the original definition that we had for electric potential energy. Right? Our potential was defined as the electric energy per charge, and now we have the vice versa being done. So this QV is the electric potential energy. So something that's interesting is we've seen Q divided by T. And in fact, we saw it really recently in the fact of the last lecture. And so we can replace Q divided by T with the current. So now we have this equation where power is equal to current times the potential. And this can be pretty useful because you're more likely going to be able to measure the current rather than the charge per time. However, what if we don't have the current? Well, we can use Ohm's law to rearrange this particular right side of the equation a couple different ways if we don't have the current or the potential. So depending on how we replace either the current or the potential, we have two new equations for power, or two new equations, right? So we have P is equal to IV. If we replace V, we have current squared times the resistance. If we replace our current, we have potential squared divided by the resistance. So we now have three different equations relating power, current, resistance, and potential. And we can use any one of these three equations in order to go through and solve. So depending on the information we have is going to determine which equation for power we end up using. So now what we want to do is talk a little bit about the household circuit. And then once we talk about that, we're going to look at an example. So that's going to take everything we kind of focused on last time as well as what we've learned so far in today's lecture. So in general, when households or living situation buildings are designed, you would like it so that your building that you've put a lot of time, money, and effort in doesn't burn down after you leave a light on for about an hour. So people go to school to learn how to design buildings so that they don't burn down from an electric fire. So power tells us how we convert our electric energy to our thermal energy. And so this is just one of our power equations. Again, we could use any of the three that we want, but we want to focus on having a current because that's something that's pretty easily measured. And in general, house wires have a very particular, like you use a couple different types of wires, so the resistance isn't too hard to figure out. So we know the rate in which stuff heats up. And so to prevent overloading, so your wires getting too hot, houses or, again, buildings have fuses or circuit breakers. So with this image up here, we have a closed circuit breaker. So you have some outside switch where you can manually open and close the entirety circuit to the home. So this is done, usually it's called a circuit board for a house. It's connected to this metal rod. And with this metal rod, if you push the switch down, it opens up this contact point, and you're going to have a circuit that is now open and electrons can't flow. If you flip the switch, the circuit becomes closed and electrons can flow. So the way that a circuit breaker is triggered is this strip over here. And it's a bimetallic strip. So there are two different metals in this strip. And so what happens is these metals, how they heat up, they expand differently. And so because they expand differently, if it gets to a certain temperature, this bimetallic strip is going to curve, and the curve is going to cause the switch to flip. So, the house is designed that if all this ends up being too hot based on the electric current flowing through it, it's going to flip the switch. And then you're going to lose power to that part of the building, whatever it's set up to. So this is kind of how a home works. So when you have that circuit board and it, you break a circuit, this is what's happening. And so here we have the open breaker. So we see that the bimetallic strip has moved over to the left, so it's curved, and it's flipped our switch. In this case, it's flipped it upwards, and again, our circuit is now broken, so electrons can no longer flow through this part or this particular circuit. And so it's just gonna basically, it's a very fancy switch designed where if it gets too hot, it's going to say, hey, let's not burn our building down. So let's think about it real quick. So with household circuits, they are set up in a very particular way. And in general, they're set up as a parallel circuit. So we're going to focus on this idea of parallel circuits next week when we start getting into them, but it's just a way that these circuits are, or the devices are set up within your circuit. So the circuit breaker looks at the total current being pulled by all of the objects for the circuit. So here we have an example of a household circuit. So we have a light bulb, an electric heater because it's cold, and we have a space heater. We've got power amplifier, and we have a hairdryer. So these might not all be in the same room, right? You can have multiple rooms on the same circuit. And so you have all these different things plugged into it. And they're all connected to the power coming into the house and to the circuit breaker. And so with this, just how the circuit breaker is part of the circuit, which is how it's able to tell if you're drawing too much power from all of your different power sources to, heat up the wires too much to reach a dangerous level. And so, depending on the devices we have attached, depending on our circuit breaker, we could technically go the entire time without actually breaking our circuit. So we might not actually need the circuit breaker because we're responsible, but it's a really good device to have there as a backup. All right, so we're going to do number 84 from the back of the chapter. It's a pretty, it contains a lot of things that we've already looked at. So before I have you guys look at some information, there's just a couple of things I want to talk about. So first off, we have a copper wire, and then in C we have a number 12 wire. This is still copper. It just has a different different diameter value. So please make sure you're aware of the diameters that you are using going through. And yeah, so just be aware that in C, it is still a copper wire. So what I'd like you to do is go through and kind of work through this particular question. Okay, so because I don't want to have to keep referencing back and forth between what we're solving, I put the parts of the question here. So the first thing I'm going to do is I'm going to write out my information so I know my current is equal to 18 amps and my potential is 220 volts. My original diameter, so that's the diameter that I'm going to be using. I'm going to in A and B, I'm going to call it diameter 1, and it's 1.628 millimeters, or 1.628 times 10 to the negative 3 meters. So in part A, I'm just solving for the power. So in order to solve for the power, I'm given the current and the potential, so I can just use my original definition that we introduced today for power. I don't have the resistance at this time, so I'm not going to be using that equation, even though I could go through and calculate it. Just right now, I don't know. In part A, I don't know the length of my wire, so I can't calculate a resistance at this time. In part B, I do have a length of a wire. I can use resistance there, and in fact, I will need to do so. So I can just plug in my numbers. Power is going to be 18 amps times 220 volts. Taking that and plugging it in, I got 3,960 watts, or that my power is approximately, because everything was given in terms of 2 sig figs, 4.0 times 10 to the 2 watts. Wait, is that 2? 3. 10 to the 3 watts. So that's part A. Now in part B, I'm given a length of my wire, and I am told it is 2 wires. So I have 2 wires, each being 3.5 meters long. So in part B, what I'm doing is now I want to find the power, but because I now have the length of my the length of my wires, I need to use a different equation. So I'm going to use I squared R. So the reason I'm going to use this one is you could use the other one where you have potential squared divided by the resistance. I just personally would rather just multiply all my stuff together. So that is 100% a personal preference in this case. You could also, like I said, use V squared over R. Both methods work. I'm just going to be using this one. So the equation that we have for resistance is rho L divided by A, where area is the cross-sectional area of our wire. So we could use either pi r squared, or we can use pi over 4d squared. So in our video or our lecture last time, I used the radius value. I would like to show you how to go through and use it with the diameter. Again, if you want to go ahead, use pi r squared here, you're welcome to do that. You just need to make sure that you use the radius and not the diameter that is given. So I'm going to go ahead and I'm going to rewrite my power equation. So I'm going to have 4 rho L over pi d squared. So this is the resistance value, but I need to remember that I technically have 2 wires. So I'm going to multiply this by 2 because I'm using L is 3.5 meters. If you want to say that the length is a total of 7 meters, you do not need to include the 2. So again, this is kind of a place where you have to make a conscious decision as to how you would like to approach doing some of this math. I know it's not exactly thrilling for me to be like, there's like 5 or 6 different ways you can set up the math to just do this question. I know that's not encouraging, but something that I like to tell my students is you're an adult, you can make decisions, so you can make a decision that makes the math the most comfortable for you as a person. All right, so now I have all my information. I can look up the resistivity of copper. It's 1.68 times 10 to the negative 8 ohms times meters. So that's from table 18.1. So I can plug everything in. For the sake of space, I am going to be dropping all of my units. So again, my current was given as 18 amps. I have 4 times my resistivity of copper, so the 1.68 times 10 to the negative 8. My length is 3.5 meters. Divided by pi, my diameter 1.628 times 10 to the negative 3 squared. So I've plugged in all of my values. Again, I'm choosing to use the diameter, so I need to have this 4 at the top here. And then because I'm using my length as 3.5 meters, I need to have the 2 on the outside to account for the fact that there are 2 wires. And I forgot the squared on my 18. So I can take all this and plug it in. I'm going to find that the power that is being dissipated in the wiring, so in the wiring itself, I'm converting 18.304 watts, or approximately 18 watts. So in A, I'm looking at the total power the air conditioner is drawing in. In part B, I have found out how much power is being basically lost purely by the copper wiring inside of our air conditioner. Okay, so now we can move on, or before we move on to C, I just want to reiterate a little bit what we've done. So we looked at the power being pulled by using the current and potential given. In B, we were given information about the wire inside of the air conditioner. So we had to calculate the resistance, and then using the current given, I calculated the power. Now you could also calculate the resistance and then use the potential. Both methods should work out to give you the same answer. I just personally don't like to divide. So in number C, or letter C, we're being asked to replace our wire with a different diameter wire. And we want to figure out how much power is dissipated in this case. So our new diameter is 2.053 millimeters, or 2.053 times 10 to the negative 3 meters. And literally everything else is going to remain exactly the same. The length is the same, the current is the same, the potential is the same. Literally the only thing that's changing is the diameter of our wire. So we can use the same exact equation we had in the previous part, so part B. So I have 2 times the current squared times 4 times the resistivity times the length divided by pi, in this case diameter 2 squared. So now I can go ahead and I can plug in my numbers. So I have 18 amps squared. I have 4 times my resistivity of copper, so that's 1.68 times 10 to the negative 6 ohms times meters. My length is 3.5 meters. This is all going to get divided by pi. My new diameter, so 2.053 times 10 to the negative 6 meters. I need to make sure that that gets squared. So I can take all of this and plug it in, and I ended up getting 11.510 watts, or my new power with my new wire is 12 watts instead of what we had in part B, which was 18 watts. So I have roughly lost 18 watts of power, or I keep 8 extra watts of power by just simply changing my wire. So in part D, we are looking at how much money we're saving by using our new wire instead of the original one. And we have some information that we are given. So our time is 12 hours per day, and we are spending 12 cents per kilowatt hour. So this is the information that we're going to be using to go through and solve. And we also have 30 days in our month. So in order to go through and find our power, here we don't have an explicit equation for what we're doing. So we're not really finding power, we're finding our money per month. So we're doing basically, in part D, all we're doing is some fancy unit conversions to go from what we know about power to a dollar amount per month. So we need to look at how much power we are saving by changing our wire. So we're going to take our original power from part B and subtract out our new power from part A. Oops. Both of these are in watts. And so this is going to give us a power part. And now we need to go through and start converting. So we know 1 kilowatt is 1,000 watts. So that's going to get us the kilowatt part that we're going to need. We're going to be going for 30 days, and every day we're going for 12 hours. I should have given myself a little bit more space. We have one more thing we need to consider, and that's the 12 cents per hour that we are using. So all of this information here, again, is just fancy unit conversion. We're going from watts all the way to, we're going to have, if we look at canceling stuff out, we're going to have kilowatts per hour, but it's going to be in dollar signs. I'm trying to figure out what happened, what I did with my kilowatts. Give me a second. Oh, sorry, it's not per hour, it's per kilowatt hour. So by having kilowatt and hours at the top, so right, we have a kilowatt, we have hours at the top. Those combined together are kilowatts. And then when we convert to money, that's going to be how we get rid of the kilowatts and the hours. So we can take all of this and plug it in, and we're going to find it's 0.2935. This is in dollars per month. So either we're saving, depending on how you want to do it, $0.29 a month or 29 cents per month just by changing our wire. I know that doesn't seem like a very large amount, but over the course of years, you know, you're going to be saving a couple dollars. So in this particular question, you know, we've used everything from this chapter up until this point to see how power and resistance can help us save money. All right, so this is going to wrap it up for our first video. Please make sure to watch the second and the third videos as well.